Okay, so I am going to be explaining 1995 E1 as the problem, and once again, the unit that we are covering is electric potential path integrals. So this AP problem isn't 100% about the path integral, but rather it's in one of the sections, and this is what you'll probably be likely to see on like a normal AP exam free response problem for E&M. So yeah, so we could just get right to it. So to start off, the first part is it says there's a very long non-conducting rod of radius A that has a positive charge distributed throughout its volume. The charge distribution is cylindrically symmetric, and the total charge per unit length of the rod is lambda. So that means that there's going to be charges all throughout this rod, on the inside, on the outside, on the surface, and beneath it, because it's a non-conducting rod. And the charge per unit will be this constant lambda. So for part A, we have to use Gauss's law to derive an expression. Okay, so Gauss's law states that the integral of E dot dA is equal to Q enclosed over epsilon naught, where epsilon naught is a constant. And since we're looking for the magnitude of the electric field, we want to isolate this E. So the first thing that we can notice is that this is a cylinder, and a common Gaussian surface for cylinders is just another cylinder. So and this is like a very long rod, so we can neglect the electric field divergence due to the ends of the rod. So if we just take if we create our own Gaussian surface, which would be like this black rod I'm drawing in, and then it would be like its own cylinder. Then all the electric field lines from this cylinder will be pointing out. They'll be pointing out of the cylinder and through the through our Gaussian surface. So that means that we can get rid of this dot product here, because E and dA will always be perpendicular to each other, so we don't have to worry about that. But the thing that we do need to figure out is what Q enclosed would be. So to find Q enclosed, we will have to use the lambda constant, which is charge per unit length. So if lambda equals Q over unit length, that means that the charge equals lambda times L. So yeah, so now if we plug this into the equation, we can get the integral of E dA equals lambda times L over epsilon naught. And now we can work on the integral part. So this integral, so E will be the same throughout the Gaussian surface, because it's going to be a constant distance away from the cylinder that it's surrounding. So we're able to take that out of the integral and just make a E times the integral of dA. And the integral of dA will just be the surface of the Gaussian surface that we will be taking into consideration. So since we are doing it over a length L and it's a cylinder, the formula for the surface area would be none other than 2 pi r L. So that means that the left side of the equation would turn into this. It would turn into E times 2 pi r L. Okay, so now plugging that into the equation again, this equation turns into E times 2 pi RL equals lambda L over epsilon naught. So if we want to isolate and solve for E, all we have to do is divide by 2 pi RL on both sides. So if we do that, we would end up with our final answer. Oh, also, some stuff cancels out. I'll show you. This L cancels out with this L, and yeah. So our final answer, we would end up getting the electric field, E, outside of this long uniform rod, this long non-conducting rod, would end up being lambda over 2 pi r epsilon naught. So that's how you do the first part. And the second part is asking, the diagrams below represent cross-sections of the rods. On these diagrams, sketch the following. So several equipotential lines in the region R equals A, and several electric field lines in the region R is greater than A. Sorry, I meant R is greater than A. So equipotential lines literally just mean draw lines where every single point on that line will have the same exact electric potential as any other point on that line. So the important thing for equipotential lines around a rod like this is that the electric field or the electric potential will depend on the radius. So as you can see from the formula we just derived for the electric field, lambda is a constant, epsilon naught is a constant, 2 and pi are also both constants. So the only variable in that entire equation is this r. I'll highlight that. So yeah, so the only variable is the r. So that's going to be the only thing that affects the potential as well. So that means that we can just go ahead and draw like concentric circles around the rod to depict the equipotential lines. And then the several electric field lines, well, that's going to be a little bit different. So electric field lines would end up pointing radially outwards, and these are going to be perpendicular to the these will end up being perpendicular to the equipotential lines that we just drew in part B number 1. And yeah, because this, you can think of it as acting kind of like a positive point charge, and all the electric field lines would be pointing outwards because because it's just a positively charged rod. And then next we have part C, which is, this is the part with the electric path integral. I'm going to make this bigger so it's easier to see. Okay, so in the diagram above, point C is a distance A from the center of the rod, which is over here. And point D is a distance 3A from the center, so that's this part. That is 90 degrees from point C. Determine the following. The potential difference VC minus VD between points C and D. So that pretty much just means find the change in voltage between points C and D. So first off, we need to figure out how we would approach this problem. So just like we looked at in point B, in part B, the equipotential lines around this rod will be like concentric circles. So that means that the amount of work it takes to move a point anywhere on its like concentric path, I guess, would end up being 0. So this point D, the potential difference between C and D is going to be the same as the potential difference between C and some other point like over here on the same radius. So if we can just make it easier and then make this point parallel to A. So that would be like somewhere over here. So now it's a lot easier to visualize how we would take our path integral. Okay, yeah, so we can just call this the new point D over here, and now we need to find the voltage or the change in potential between C and D. So to do this, we can use our electric path integral. So if you remember, the formula for that will be the change in V from point C to D will equal the negative integral from C to D of E dot dl. Yeah, E dot dl. So if you go back to part A, we can see that we can look at our E and just use that. So we got E equals lambda over 2 pi r epsilon naught. So we can just plug that in for E. So that's the same as equals the integral. And point, when I say from C to D, that's the radial component, or the radius, so that would be from A to 3A pretty much. So we can just keep that there. Of lambda over 2 pi r epsilon. 2 pi r epsilon naught. And then dl. And what we can do now is actually change this dl into a dr, because if you look at this diagram again, the radius away from the center of the circle is going to be the same as the length, or the dl's, that we're going to be integrating through. So we might as well just change this dl into a dr so it's easier to work through. So now we can take the constants out of this integral, and the constants in this would end up being the lambda. Oh, whoops. Sorry. The constants would end up being this lambda, the 2 pi, and the epsilon naught, which is pretty much everything except this variable of integration. So now if we take these out, we would end up with negative lambda over 2 pi epsilon naught times the integral from a to 3a of 1 over r dr. And now this is an integral that we all pretty much know how to take. 1 over r integrates into, the antiderivative of it is just ln. So then the bounds would end up being, it would become negative lambda over 2 pi epsilon naught times ln of 3a over a, which ends up just becoming 3a, oh sorry, just 3, because the a's would cancel out. Let me erase that. So that just becomes times ln of 3. Yeah. So that is what the change in potential from points C to D would be. And then part 2 of that is just the work. And the formula to find work is just work equals Q times delta V. So we would just multiply what we just got by Q. And that would end up becoming negative Q lambda. Yeah, negative Q lambda over 2 pi epsilon naught times ln 3. So now for the final part, we would need to find the magnitude of the electric field for this function of r if the charge density is rho. And this would be dependent on volume, not just unit length like lambda was. And it's going to be changing. It's not constant like lambda was either. So what we have to do here is Gauss's law again. And since this is inside the rod, I think it would be helpful if we drew like a diagram. So if this is the rod facing us, then what we want to do is we want to find the electric field for a radius that's less than r naught, which would be like the radius of the entire cylinder. So our Gaussian surface would end up being like a cylinder that would be inside the other cylinder. So so we can just start off with just setting up the formula, which is E times dA, E dot dA, integral of E dot dA equals Q enclosed over epsilon naught. And now for this, the difficult-ish part would be finding Q enclosed. So we can move the epsilon naught to the other side for simplicity's sake. And then we can just integrate this integral just like we did before. So we can move the E out because it's going to be constant everywhere on this Gaussian surface. And then the dA, that'll just integrate to 2 pi r L, which is the surface area of our Gaussian surface. So then this would become E times 2 pi r L times epsilon naught equals Q enclosed. And the reason is because as the radius goes out more and more and more, our density will change. So to find the amount of charge enclosed, we'll have to integrate the density function. So that means that Q enclosed will end up becoming integral from our initial radius, which is 0, to our maximum radius, which is r, of this density function. So that would just be integral of rho naught times r over a to the power of 1/2, and then times dr. Oh, sorry, no. It would be this times 2 pi r L dr, because this would be the density, and to find the charge, we'd multiply the density by the volume. So that'd be 2 pi r L. Okay. So now what we can do is we can just solve this integral. So I'm not going to work out the entire thing because it's just going to be a lot of algebra. But what we end up getting is the left side would end up becoming the same. It would just be E times 2 pi r L times epsilon naught. And then the right side would end up becoming integral from, it would end up becoming rho naught over square root of a times 2/5 r to the 5/2 times 2 pi r L. Sorry, the r would go away when we integrate, so it just becomes 2 pi L. And from this equation, you can see that there's a few things we could cancel out. Cancel out the 2, the pi, and the L on the both sides, 2 pi L. And then what we're left with, again, we're solving for electric field. We just have to divide by epsilon naught times r, and we'll get E equals 2/5 rho naught r to the 3/2 over square root of a times epsilon naught. That is what it would